We'll start off with a presentation by Ian Flint, who is with Lab 4, which is partnering with Graphite One to design and build a new lithium-ion battery recycling facility in Washington, bringing the full circular economy to the graphite supply chain as I understand it, and really eager to hear from Ian. Ian, it's all yours.
Thank you very much. Just a little bit about myself to begin with. I've been working in the battery materials space for about 30 years, both in the primary source of them, which is the mines, and also in recycling. And we've worked in basically every single material that's in it. I am the engineering director and partner of Lab 1. And we have partnered with this particular project with a company called Graphite One Alaska, who have a large graphite mine in Alaska and are planning to build an anode facility in Washington State. And you'll see later why Washington State is right at the end, so you can be patient for that. Anyways, next slide, please. The basic problem with battery materials, at least in the United States, is that none of it is actually mined in the US. And there's already small limited resources that are fully stretched to supply the batteries that currently exist. In the next 10 years, there's anticipated to be a 500 times, 500% increase in the demand for these materials for these various batteries. This brings up a huge conundrum, which is where are we going to get these materials from, and how do we ensure that any risks associated with countries that are producing it at the moment, so for example, 75% of the graphite is produced in China, how do we limit those risks? And so what I have done is we have worked on the primary sources of all of these, manganese, for example, and lithium and graphite. But for the last 4 years, we have also worked on the recycling. The processing of recycled batteries is actually quite similar to what you do in the primary processing. Next slide, please. There is about $1.75 worth of materials in every battery. This is about 40% of the value of batteries. Now, I'm rounding up here in even numbers so that it's not quite exactly right. The projected amount of materials that are required for batteries by about 2030 is about $20 billion US. It's a serious problem because I said already the amount of materials for batteries is already stretched to basically market capacities. Next slide. So that brings up, what do we do? And the first answer is recycling. What you see here is what the contents of a ton of batteries are. Now, this assumes what battery called the typical battery that you can call an 18650, and just the stacks and stacks of these go into a Tesla car. And you can see that for every ton of these batteries, there's about $11,500 of materials in that. And the distribution of the different metals in it are given in this pie chart with cobalt, copper, graphite, nickel, manganese, and lithium. Now, this isn't any particular kind of battery because there's all sorts of different cathode configurations, which will give you a different percentage of minerals. This is basically a conglomerate of an average of all the different cells that are out there at the moment. So it may not say this way. So what we have to do is we have to somehow recover this material and reuse it. So next slide. So this is the 3 ways that we can rescue ourselves from this situation. One, we can increase the primary production. This is mines. And we at Lab 4 do that already. We consult for a lot of different companies that are producing this kind of material. But as I said before, that's not going to be the answer. So we have been working for almost 5 years now on the recovery of these materials from batteries. And what we've done is we've looked at what the downfalls of the other recycling processes are, and we've tried to answer them. Now, just for completeness, there's also reuse of batteries, which is that how do we reduce the total number of batteries that we're using? And the way to do that is to take aside any batteries that don't need to be recycled and repurpose them for other things. That's down the road. We're starting to work on that now, but that's still 2 years away. Next slide. This is what current recycling methods do. This is the state of the art. Not the conventional stuff that's practiced in China where they take them apart by hand and try to unroll it and rescue everything as possible. But this is what the typical European, North American factories can do on recycling. They can recover about $7,500 per ton of that 11,500. And you can see from the pie chart there that most of the lithium is recovered. Now, the area of these two charts, by the way, is proportional to the value. So you can directly have a look at that. Almost all the copper is recovered. The cobalt, not so good. So what do we do? Next slide, please. This is sort of just a general chart of what's happening as you go from fabrication to use. And then if you look at the chart or the diagram on the left, this is with the metals in the battery. I'll deal with that first. Right now, very few of these batteries are recycled, 2 to 5%, not much more than that. So that the arrow that's going directly horizontal from use is the stuff that's basically just going to landfill. However, the rest is recycled. And of that, you have those recycled metals that go back into the process and you have the residual. So the recycled minerals is that 7,500 I talked about, and the residuals is the rest. Right now, if you look at the right side, is the graphite. None of the graphite is recycled. It all goes into what is called this carbon residual. And that's where we have concentrated our research on. Next slide. As you can see, what we're doing, we put another process in here for the residuals. So that you go through recycles and residuals, and we catch that stuff. We can recover 95 to 99.9% of the materials that are left. And we can recycle that to fabrication. Graphite is another question. As you can see, I've got 2 arrows there. And depending on the battery, we can recover the graphite, but we may not be able to reuse it in batteries. And that would go to replace some of the primary source graphite in other applications, freeing it up for batteries. So it's not lost. Anyways, as I said, this has been the concentration of our work. And you see the next slide, please. You can see with the next slide where our little pie chart comes in here, which is we recover the 3,000 and change to bring it up to almost an entire recovery of what's in the batteries. This is essentially a game changer because it eliminates the carbon residual, which is a waste product at the moment, considered to be basically a dangerous good. It's all the right stuff in the wrong place. So we were recovering that and putting it back into the circular supply. Next slide. I'm going through this really fast, so we're going to have lots of time for questions. I originally referred to the 20 billion at the top, which is the amount of materials that's expected to be in use. That's the total materials. Of that, the conventional recycling, we're kind of recover about $30 billion of stuff. The residuals that we recovers another 6 billion, which means another billion has to be put in from primary resources. And that 1 billion is actually already stretched in the current market. It'll be interesting how to get there. We're going to, as I said, we're going to be in for a good time. I don't exactly believe all these forecasts simply because the material is not going to be there fast enough. Next slide. And this is my final slide. And this is what I'm going to be talking about, which is why Washington State. If you look at this, you can see that the batteries are going to be collected from wherever they're used. And most of these batteries we're talking about are from vehicles. So most of them will have to be collected in populated areas. Batteries are considered to be a dangerous product. Therefore, they're not supposed to be transported very far distances. Getting them across state lines or getting them across country borders was very difficult, which means your recycling plant is going to have to be located close to those concentrations and populations. So whether that's Seattle or whether that's Washington, D.C., or whether that is Toronto, Canada, or whether it's Paris, France, that's where that is going to have to be processed. And there's really not much way we can get around that unless all the countries started changing the rules, which is not about to happen. The residuals plant, on the other hand, has no restrictions because that carbon residual is not a dangerous waste in terms of transportation. It's got a lot of stuff in it you don't want there, but we can get that all out. The cathode plant, where all these materials go to, has to be in a place where there's cheap electricity, because one of the stages includes a lot of electrical use. Battery assembly, which is the next step, there's no restrictions on, you can do that anywhere. Battery installation, obviously where the automotive assembly plants are, and they have their own criteria of where they're going to be placed. And then back to the battery use, where the batteries get spread all over the place. So you say to yourself, where are we going to put our residuals plant? And the recycling we can do at the same time, because we can do both. And the answer is it should be close to the anode facilities, just to save as much transportation as possible. So that's what we have intended to do. And one of the reasons that we've partnered with Graphite One, because Graphite One is starting an anode plant in Washington State. So not only is it close to the anode plant, but it is also in, sorry, you have to excuse that. Not only is it close to the anode plant, but Seattle is there. You have a lot of recycling right from there, right from the local source. So that's what we intend to do. If you go next slide, please. And that's it. I could talk about this topic all day for anybody who's really interested. But we only have limited number of questions that we can ask. So please ask away.
Thank you, Ian. Super fascinating. And I have to admit, 100% educational for me. I know nothing about this, but it begs a lot of questions for me. I guess first, how close are you and Graphite One to establishing that those facilities here?
We have done all the lab work. We are putting together a pilot plant where we will test for engineering data. The technology is proven, but we still have to figure out, how the equipment is going to work at different sizes. The pilot plant should take about 18 months to come to a conclusion. We are designing the full-scale plant in parallel to that. So we expect to start building that in before that 18 months, take about a year to get finished. So the earliest timeline is approximately 2.5 years.
Okay. Did I hear you correctly that close to 100% of the batteries will be able to be recyclable?
Lithium-ion batteries, yes.
Lithium-ion.
There's an interesting program going on in China right now where the battery manufacturers are required by law to retain the liability of all the batteries that they make,
Okay.
Which means they make sure they come back. That almost has to be done here. And if you do that, we should be able to recycle almost all the batteries. The aluminum industry right now, the aluminum is like 95-97% recovery of aluminum. So there's no reason we can't do that for batteries.
And is that circular as in battery to battery, or is it some goes back into batteries and some goes into other applications?
It's an open market. In other words, if you make the cobalt, anybody who wants to buy the cobalt can buy the cobalt. But those industries have been rather static for quite some time. The need for cobalt isn't going to change. So it could be circular. And there's things in the works where the major car companies are going to want to reclaim their batteries, recycle all the material to put back in their batteries. So it could very well be circular.
Got it.
Aaron, you have an
There's a
audience
question in the chat. Yeah, I see that. 1 minute left and there's a question in the chat. Are there health or environmental concerns associated with operating a battery recycling plant, especially near populated areas?
Not particularly. There is no discharge whatsoever with this. Everything is totally within the plant. The materials that are toxic in the batteries are of limited toxicity comparison to previous batteries, like the old nickel cadmium batteries that we used to have. So they're borderline toxic waste to begin with. The carbon residual as it is currently produced is considered to be a toxic waste. And we will get rid of that. So this is a zero discharge plant. There's nothing in the air that's going to be affected. It's a pretty clean process.
Okay, I believe we are at time, but there are some questions that you could answer. I think you can answer yourself in the Q&A, Ian. yeah, about silicon carbon composites and anodes. And so
We could probably talk for 4 hours.
thank you. Thank you so much.